This video covers Leslie matrices. Now, generally, it's not possible to predict a rate of growth of a certain population of animal based on the size of the population alone. A Leslie matrix models the growth of the female portion of a population, and it uses survival rates, which is the proportion that will survive until the next year or the next time period, and the fecundity rate. And that fecundity rate is the actual reproductive rate, or how many babies are produced each time period. Now, that's only going to be for the females because the females are the ones that have the babies. Now, a more accurate picture of survival rate can be obtained if we use survival rates specific to the different age groups. So, what I mean by that is we don't say the survival rate of a possum is 0.6 overall. Okay, the survival rate is different depending on the age of the population. So maybe your babies, you lose more of those, but once they hit a certain age, then the survival rate goes up. For example, then when they get really old, the survival rate goes down. So splitting a population into smaller age categories and looking at the survival rate of each age category will give you a more accurate population model. Now, the use of Leslie matrices is a form of population modelling. Now, like all population models, the Leslie method is based on certain assumptions. One such assumption is that those survival and fecundity rates that we use will remain constant over time. Now, in reality, that's probably not going to happen, and they may even fluctuate as a result of environmental factors, availability of resources like food, and the presence or absence of natural predators. Now, the process of using Leslie matrices, as already said, we're going to divide the population into age groups. Now, each age range has to have the same length, and together they cover the lifespan of the population. So only the females of the species are counted in the population because they're the ones that have the impact on birth rates, for example. So their fecundity rates is dictated by females. Example of age groups for a study of a human population, if we were looking at 0 to 110 as being our age range of the human population, because we need set same lengths for each age range, we might go for 10 years. So 0 to 10, 10 to 20, 20 to 30, etc., all up to 100 to 110. So that'd be 11 different age ranges. And then we would look at the survival rate and the fecundity rate for each of those age ranges. Now, survival rates, which we'll use as S-base X, for an age group X is a proportion of the population in an age group X, a progressed age group X plus 1. So what that means is what proportion, if we're looking at our female human population here, like that I've got in this table, what proportion in age group 1 will move to age group 2? Okay, what proportion of age group 2 will go to age group 3? So that's called our survival rate. Now note that that survival rate needs to be between 0 and 1. And also the survival rate of the last group is taken to be 0. So looking at this table for humans, we're saying there is no survival beyond 100 to 110. Now, fecundity or birth rates, we ignore migration. So the population growth is entirely due to new female births. Now, note, again, we're looking at the female population. We're looking at the female births. Now, the fecundity or birth rate, F-base X, for age group X is the average number of female offspring per female in age group X during one time period. Okay, so average number of female offspring per female. So we're only looking at female births, we're only looking at females. Let's look at an example. A wildlife officer is interested in the number of a certain species of rat in a habitat and has compiled the following information on the species. So we have population here, age, at year end, so 1, 2, and 3, and we have the number of females, 55, 32, 25. Now, it is assumed that rats don't live longer than 3 years, and that there is the same number of males and females. Okay, so this same number of males and females is something we need to look at if all we're looking at is the females. Fecundity rates, F of X, the number of female offspring per female per year. So for age group 1, that's 0.6, age group 2 is 2.4, and age group 3 is 0.5. And then the survival rates, S base X, of each age group has also been estimated. So for age group 1, we have 0.5, and for age group 2, we have 0.6. Remembering that we assume that the last age group does not have a survival rate. That is the final, and that's why we said that it's assumed that rats do not live longer than 3 years. Now, note that 1-year-old rats that survive the year become 2-year-old rats. Okay, 2-year-old rats that survive the year become 3-year-old rats. So as each age group of females produce babies, the number of 1-year-old rats in the next year can be calculated at. We get the number of 1-year-old rats is going to equal the number of 1-year-olds times the fecundity rate. Okay, how many female offspring a female's had per year, plus the number of 2-year-olds times that fecundity rate, plus the number of 3-year-olds times that fecundity rate. Okay, because our number of 1-year-olds are what's being produced by the population that's already there. Now, the number of 2-year-old rats in the next year is going to be 0.5 times the number of 1-year-olds rats. So that 0.5 is the survival rate of 1-year-olds. And the number of 3-year-old rats in the next year is going to be 0.6, which is a survival rate, times the number of 2-year-olds. Now, this process seems very confusing, probably, but it can be simplified by using matrices. And you may have already thought about that when you saw the tables. So if we look at population end of year 1, we could express that as a matrix. It's a 3 by 1, 55, 32, and 25. And we can also come up with our Leslie matrix, which is going to help us with our population modelling. Now, our Leslie matrix has a certain setup. Across the top row of our Leslie matrix, we put the fecundity rates. So 0.6, 2.4, and 0.5. And then we need our survival rates. So it's 0.5 for our 1-year-olds. And then we put in our 2 zeros. And for our 2-year-olds, it's 0.6. Remembering that our 3-year-olds do not survive beyond. Okay? So just color coding that, we have our fecundity rates going across the top. We have our survival rate for 1-year-old and our survival rate for our 2-year-old. Now, if we want our rat population at end of the second year, our N2 is going to be our Leslie matrix times by our N1. So that's going to be 0.6, 2.4, 0.5, 0.5, 0, 0, 0, 0.6, 0, times by N1, which is 55, 32, 25. Now, with your Leslie matrices, chances are you're going to be doing a lot of this on the calculator, especially when we're going to be looking long term. So go to your calculator, and because we would be looking long term, you would assign that Leslie matrix as something in your calculator so you can use it over and over again. So that's what we get when we do that multiplication. So our total female population is going to equal 122.3 plus 27.5 plus 19.2, and that's 169. This is where we assume equal numbers of males and females. Our total population would be equal to 169 times by 2, which is 338. Let's look at another example. Consider a species with a lifespan of 9 years split into 3 age groups. So because we need equal numbers in each age group, what we're going to have to do to go across 9 years, if we have 3 age groups, age group 1, 2, 3, we'll go from 0 to 3, 3 to 6, 6 to 9. So there are our 3 age groups. Now there are 400 females in each age group. And then we have our survival rates and our fecundity rates. What is the initial population as a matrix? Our P0 is going to be 400, 400, 400. Okay, so that's for age group 1, 2, and 3. Bit straightforward since they're all the same. What's the Leslie matrix for the 3 age groups? So remembering from the previous example, the 3 fecundity rates go across the top. We have our survival rate for the first one and our survival rate for the second, and then everything else is a 0. So for this example, we're going to have 0, 2.3, 0.4, 0.6, 0.3, and then everything else is a 0. Okay, so we can now use that to find group sizes. So group size at end of first 3-year period is going to be a Leslie matrix multiplied by the initial. So 0, 2.3, 0.4, 0.6, 0, 0, 0, 0.3, 0 times by the 400s. And that will give us 1080, 240, and 120. If we wanted the end of the second 3-year period, P2 would be our Leslie matrix multiplied by P1, so what we just found. So that's going to be 0. So you can see why it is worth in your calculator assigning that Leslie matrix, because you could end up using it more than once. Okay, and going to your calculator, you get 600, 648, and 72. And you can see in this table a number of time periods being done. Now, question, can you identify a quicker way to calculate the population instead of 3 years at a time? Okay, what if I wanted to know what the population would be at the end of time period 5 without having to do all the other ones first? Fair enough question, because it would be quite tedious.